insight for moving us forwards. So I would like to introduce Professor David Lariviere. He is a full clinical professor and director of the FinTech Lab at the University of Illinois at Urbana-Champaign in both the industrial and enterprise systems engineering and the finance departments, where he focuses on the technology underpinning modern markets. He previously taught in the computer science and electrical engineering departments at Columbia University and New York City, and teaching FPGA development and custom ultra-low latency networking. So David, take it away.
Thank you very much, Paul, and thank you everyone else to joining this call. So the purpose of today's lecture, or I guess discussion, depending on what we want to call it, is the race to zero and the lessons of latency. And so the greatest advances in human history often come out of the greatest competitions. And so before we get into the topic I'll be covering, I just want to reflect briefly on some of the historical past great races. One of the most importantly, obviously, is the race to split the atom.
Hey, David.
Yes.
Are you sharing? Are you sharing?
Thank you.
Okay.
I am not, and I will be in a moment.
Thank you very much.
Thank you. Now let me just rearrange my windows. Everyone can see my screen.
Looks good,
David.
Yep.
We're good. Okay. So 1939, German scientists first split uranium. 1942, the United States launches the Manhattan Project. The first self-sustaining nuclear reaction is achieved at Chicago Pile 1, a few miles from where I'm presenting to all of you. And then obviously in 1945, the first atomic bombs are created and detonated, ending World War II. But there were many revolutions that came from this atomic race. ENIAC, one of the first general purpose computers, created originally, I believe, for doing artillery solutions, but was later used for calculating nuclear reactions. The Chicago Pile 1 created the very first world's nuclear power plant, something we are looking to lean on exponentially as we continue to build out data centers for the purposes of the artificial intelligence. Nuclear medicine. We developed nuclear safety standards, cancer, radiation treatments, nuclear contrast agents for imaging for things like PET scans and MRIs. And of course, something near and dear to those in finance, Monte Carlo methods, statistical methods of evaluating potential outcomes. These methods are used to protect literally trillions of dollars today. The nuclear arms race also led to yet another great race, the race to space. Starting with Sputnik in 1957, a wake-up call to the United States that we realized we were suddenly behind. Some were calling the news in the last few weeks with DeepSeek potentially a similar moment to big tech here in the United States. Bell 101, this was in the late 1950s, the first modem that allowed digital communications over analog phone lines. But again, this was originally developed for a continental United States protection system integrating radar. Later on, we get into the Apollo missions, the first integrated circuits. Because of the requirements of going into space and requiring very, very lightweight machines, this led to the integration of circuits. And then later also as well, the ARPANET, the precursor to today's internet, connecting major universities, research labs, and military installations. This presentation is a story of another such great race. It's what we call in the financial algorithmic trading industry, the race to zero. Zero being our theoretical reaction time from when we receive information to when we are able to put bits on the wire reacting to it. And so my academic background, I don't need to cover because Paul already did. So first, I'd like to kick this off with a thought experiment. Imagine how differently you would drive your car if you could only adjust your speed every 10 seconds. You could only open your eyes once a minute. You could only start or stop the car once an hour. The speed and granularity at which we can and are allowed to react to new information determines our ability to safely and precisely control complex systems. The global financial system is one of the most complex control systems on Earth. And this is something most people don't realize or really think about. What we're really doing is a PID controller on the cumulative value of every single asset, contract, derivative on Earth. Latency is therefore critical in ensuring the proper functioning of markets and the greater society that those markets served. So because of this, financial technologists have invested extreme amounts of effort and capital to optimize latency within the financial system. So we'll go through a brief history lesson of automated trading and the advances in technology. Circa 2000s, Windows dominates the tech stack. C++ is ubiquitous for pricing algorithms. Java is beginning to go on the rise because of concerns about safety and memory bugs. Linux is really just starting to get established as a commercially viable and reliable solution. The internet is suddenly the problem. Everyone has different latencies to market centers, creating unfairness. People worry about how close their building is to the exchange they're trying to trade on. They worry about which internet service provider they may be using and if someone else has a faster link. The solution is what we call co-location, the ability to locate traders' computers in the same data centers as the stock exchanges, and then getting direct fiber optic links connecting their computers and systems to the systems of the exchange, completely eliminating the internet. This is actually a site built by one of my former students. It's called hfttracker.com. And you can actually see, and I'll mention these later, the different types of wireless links that are used to also connect these. Speaking of which,
we don't
so
see
one,
the picture, David. We don't see the tracker.
what do you see? Am I only sharing one tab? One sec. Let's try this again. All right, do you see a slide that says co-location? Anyone?
Yes, we see that slide.
Okay, and do you see this? A map of the United States?
I see that now, yes.
Yes.
Okay, all right, we're good. I don't know what was going on before. Maybe it was a time lag. The latency isn't as good. Oh, the irony. Co-location prevents systemic unfairness in markets. It improves reliability and security by removing third-party internet service providers in the critical path, but most importantly, it dramatically reduces the latency between when different trading firms get information from an exchange and then are able to react and update their prices in response to this new information. Problem now, customers now need to connect their computers across different data centers spread out across not only the United States, but the globe. And so this is an example from one of the major providers, McKay and Quincy Data. This is their offering of various wireless links connecting the major sources of liquidity and trading across the United States and across the globe. And you can see that here, for example, this is what we sometimes refer to as the triangle, with MAWA containing NYSE, Carteret containing NASDAQ, and the rest in the series of Equinix data centers in Secaucus. And between all of these are a series of redundant ultra low latency wireless links to bridge them. Similarly, we also use microwave for long haul transport across land masses. And one of the single most important is connecting here 30 miles west from where I'm speaking to you in Aurora, which houses CME's data centers. These are the set of computers that basically determine the price of the US stock market. Another solution as well is we utilize dark fiber connecting these paths. Fundamental problem, though, what is the speed of light? Actual problem, what is the speed of light through a particular medium? The speed of light through a fiber optic cable is approximately 60 to 70% of that in a vacuum. The speed of light in air is closer to 99%. So we use dedicated microwave, millimeter wave, high frequency, sometimes called ham, and even low Earth orbit satellites to connect these different data centers. And then typically within them, if you really care, you even use hollow core fiber. So context note, microwave networks date back to at least the 1950s. AT&T used to use some of the very same towers to connect both voice and transmit TV across the continental United States. HF, high frequency, dates back more than 100 years, pretty much at the invention of radio. Dedicated circuit-based networks with things like the Thomas Edison ticker tape date back more than 150 years for distributing market data. Potential lesson, sometimes much older technologies are actually far superior to newer ones. Status, suddenly the bottleneck at this point in the evolution of fintech, is not getting packets between locations. The software stack has now become the bottleneck. So the solution, coders port from Windows and Java to Linux, C++, and even potentially assembly. Why Linux? You suddenly have complete visibility into the tech stack. You're not fighting against a black box that you can neither see, nor control, nor modify. You have the ability to precisely analyze all sources of latency, both within one's own code, but also others. And you have the ability to modify it where necessary. Lesson: when performance is critical, hiding details from your customers is not the solution. Lesson: don't be afraid of your customers doing your job sometimes for you. Give them the tools to make things better, faster, simpler. Often it is dramatically easier to improve one's own code when they can see the code of the vendor systems they're interacting with. And for the record, this doesn't just apply to software, this also applies to hardware. Chiplet lesson: what kind of external probe points can we provide to customers to monitor latency within the package? This is always one of the problems when we try to do things on x86. We can't actually go in internally and probe at the hardware level exactly where the latency is. So now suddenly the user's code is no longer the latency bottleneck. The Linux kernel itself becomes the bottleneck. Switching from user mode code to system kernel mode, processing interrupts, and then back is extremely expensive. Solution: kernel bypass. Round trip wire-to-wire latencies suddenly go from 10 microseconds to 4, all without changing a single line of your software code. Bypass allows user space applications to directly read and write to the NIC's memory space, bypassing the kernel for both sending and receiving packets. A tale of two kernel bypass modes. So at one point, approximately a decade ago, they released two primary vendors: SolarFlare, that was later acquired by Xilinx, which is now part of AMD, and Mellanox, which was purchased by NVIDIA. OnLoad had slower performance, but it went on to dominate the market. They had something like 90 to 95% market share for anybody in the financial services space, both trading firms, exchanges, investment banks, you name it. VMA sort of fell by the wayside. The apparent lesson in this case was, for those somewhat critical clients, simplicity can beat out technologically superior but overly complicated solutions. So another lesson: security protection mechanisms, like the separation of user versus kernel, can be a massive source of latency and therefore waste. Next level. Suddenly now the software was no longer the bottleneck. The hardware was. So where in the hardware? Most people obviously would assume it's doing lots of complicated math. Of course, it's going to be in the CPU. Wrong. Specifically, it's in the PCI Express bus. Many trading strategies can pre-compute their intended reactions to different possible scenarios ahead of time. We can then decide with a single logical operation how to adjust countless prices around the globe. Essentially 2 lines of code. If this, send these. Suddenly getting data on and off the wire is the vast majority of the latency. Even today in 2025, the PCI Express bus overwhelmingly is the largest source of latency in elite x86-based trading systems. And from what I understand from the specs of the performance of the CXL cores that may be coming down the line, they still have massively higher latency than those in the financial services place have been able to achieve on similar types of scenarios. Solution: move the PCI Express controller from the North Bridge and into the CPU socket. This was Sandy Bridge. Suddenly latency goes from 4 microseconds to 2. Now NUMA becomes a much bigger issue. NUMA solutions essentially throw out the last 40 years of computer science. Algo coders will completely replace the Linux kernel, from allocating memory, scheduling threads, assigning interrupts, you name it. Lesson: eliminating hops dramatically improves performance. This is a lesson we're going to see time and time again. The single best way to improve the latency of a particular component, program, algo, or device is simply to delete it. And so as a visual, this is from Elon Musk's SpaceX, and you can see the evolution on the left of Raptor 1, Raptor 2, Raptor 3. Simplicity is our friend. Even with Sandy Bridge and integrated PCIe controllers on socket, the latency is still the overwhelming bottleneck. Solution: high-frequency trading firms were forced to build their own custom hardware, starting with using FPGAs. And so we can go through, and this has now gone on for quite some time. And at one point, they actually hit the issue where the SerDes, even on the FPGAs themselves, suddenly became the bottleneck. And thus firms, even if they were relatively small, started doing full-blown ASIC, even if you only need a single chip. This is essentially unheard of in the vast majority of other industries. And so the current state of the art now, and in response to this, was that Xilinx created the Alveo UL3524. And basically, this is a custom spin with lower latency SerDes for getting bits on and off the wire faster. And so what this suddenly allowed is, at least in some cases, you could still be competitive doing FPGAs and you no longer had to go the ASIC route. So if we can do Ethernet in 3 nanoseconds, why not use it everywhere? Some questions. We generally treat memory as a definitive method of I/O. Why not make Ethernet a first-class citizen and general-purpose CPUs, similar to memory reading and writing instructions? Or similarly, can we even replace reading and writing to memory as just another method of sending Ethernet frames and receiving back the results? Why have so many different electrical engineering signals at layer 1 and layer 2? We have DDR, PCIe, CXL, HDMI, Ethernet, InfiniBand, fiber channel, etc. Why can't we just choose one, and one that we know works? What could become possible if every Ethernet SerDes was cheaply capable of receiving many wavelengths? We spend gigawatts of power serving photos of cats, people, celebrities, etc. How many components, devices, routers, switches, CPUs, FPGAs, storage devices, operating systems, virtual machines, containers, etc., have to be in the critical path to simply serve up a photo of a cat? 50? Can we do it in 2? Right now, the way we architect and design these systems are massively unnecessarily complex. And the result is poorer performance, but worse, massive waste of electricity. We as a society are spending billions on electricity to operate modern data centers. What lessons from this great race can be applied to these to massively reduce latency and, more importantly, power consumption? This is not a hypothetical. The cost of energy has grown dramatically in recent years. It is not only measured in dollars, it is measured in blood. And we see this in areas like Ukraine and others. Have we spent too much emphasis over the last several decades making the engineers' lives easier rather than building more optimized systems that require more work and a deeper understanding of the entire software, operating system, hardware, and networking stack? This is the takeaway from algorithmic trading. You have to understand, control, and optimize everything. Black boxes are not allowed. What role will LLMs play? This presentation started by talking about great races with even greater importance. And so I'd like to end it on yet another race. And so, as we know, around the United States and around the globe, different companies and countries are competing to achieve what we sometimes refer to as AGI. This, I would argue, is the single greatest race we as a species will ever pursue. Humanity is currently engaged in this race. Some refer to it as our final invention. The basic implication being that once we achieve this, it will do the future work for us. If this is our final invention, then the race to achieve AGI will be our final race as a species as we exist today. And so this year also marks the 80th anniversary of several critical milestones. It is the end of World War II. It is the race to split the atom and build the first atomic bomb. And from that came Bretton Woods and the modern world economic order. Now, putting away my professor of electrical engineering and other engineering hats and putting on the finance hat, this was a profound development in recent history. What this essentially did is establish a global framework of security, collaboration, and friendly competition between countries. It is the world order that has allowed us to have some of the greatest innovations in the last 100 years. It enabled an extraordinary period of development, achievements, and uplifting billions of people out of poverty. But a lot of it comes back to the simple point that the United States got the atomic bomb first. And so we were given the privilege to write the rules that determine the next 100 approximately years. Whoever or whatever first develops artificial general intelligence will suddenly find themselves with a similar but much greater power than what the United States was enabled with with our creation of the atomic bomb. They or it will write the next set of rules of the world order and of the human race, not just for the next 100 years, or possibly even the next 1,000, but the final set of rules that we may be guided by as a species as we exist today. The people on this call and working in these areas, whether they realize it or not, may be part of that very effort, that grand last race. And so let's make sure the right side wins. Ethernet may be a critical component in this endeavor, both from a latency, performance, and cost perspective. And so are all of you. So it is a privilege to meet everyone. Paul, thank you very much for this privilege to kick off this initiative. I'm enormously looking forward to future discussions on how we can optimize computing and ensure that we are the ones who win this last final race. Thank you very much, everyone.
David, thank you. Excellent. I was really